Okay, so today we want to talk about implicit differentiation, but to start with, let's just really look at what this dy over dx means. Okay, because if I give you this nice polynomial function, y equals x squared plus 4x plus 9, ask you to find the derivative, a lot of you probably just say y prime equals. You might say dy over dx, but just read it as just the derivative. But what this really means is y is a function of x, correct? Like x is our variable, that's our input, our independent variable, and then y is a dependent variable. It's an output. It's based on what that input is. Okay, so what's happening is the y is really doing the same thing that u did when we did chain rule. So what we're saying is we don't, just looking at the left side here, we don't know what y is, so its derivative with respect to x would just be written as dy over dx. Okay? That's what we're doing. It's nothing magical because the y is by itself, and we're going to see that today. So here we know y is a function of x, but for its derivative, we just say it's going to be dy over dx, right? Or the derivative, you might also remember sometimes we would write that as the derivative with respect to x of y, correct? It's just saying we're taking the derivative. We're using x as our independent variable. Right? Y is based on that. It's dependent. So here this would give us what? 2x plus 4? We all had that? Yes?
So then what is the difference if you do like dx over dy instead of dy over dx?
If you flip them?
Yeah.
Okay. So the question was, what's the difference between dy over dx compared to dx over dy?
Or just like y prime. Like if you're just finding y prime.
They're all different. Well, this is the same as y prime.
Yeah.
This and y prime all mean the same thing, right? So if you saw dx over dy, which you rarely see because it's really confusing to look at, but this is the derivative of some function x based on the input variable y. So it's kind of strange. Okay, a better way to look at it is like if we think back to our velocity acceleration position, there a lot of times we would have, I don't know, here a velocity equals 2t squared plus 3, right? But we want to take the derivative of velocity as acceleration, correct? But it's the derivative with respect to time. So t is the input variable. So we say dv over dt equals 4t. Right? So that bottom is telling you what we're taking the derivative with respect to. So you really would hope to never see dx over dy because it's horribly confusing looking. But yeah, very good. Right. So we're good on that one? Now, what would this one be? This is the same function. I just subtracted y from each side and subtracted 9 from each side, apparently, right? But could you take the derivative when it's written like this? Sure. You're going to take each term, you're just taking the derivative with respect to x. So not that we ever would write this much out, but you're taking the derivative with respect to x of negative 9 equals the derivative with respect to x of x squared minus the derivative with respect to x of y plus the derivative with respect to x of 4x. This is what you've always done every time you do a derivative. You just don't ever write it like this. Well, what's the derivative with respect to x of a constant? 0. The derivative with respect to x of x squared? 2x. Because with respect to x matched the variable, it is 2x. Now, what's the derivative of y with respect to x? Well, as it's written, we don't know what y equals, correct? So we just use the notation. We say, well, minus. We usually write it as dy over dx, but we know that means the same thing, correct? Again, because this was not an x, so we couldn't take the derivative normally. We're actually using the chain rule here, is what's going on. And then over here, the derivative with respect to x of 4x would just be 4. Right? So then if we wanted to solve for dy dx, could we add this to both sides? Sure, we could say dy over dx equals 2x plus 4. So you get the same thing, right? It's that same process, but it's just that with respect to piece is why it was annoying to write it. I'm sure it was annoying to put up with it when we were writing out chain rule or product and quotient rule, and I kept doing all the differential notation on there. It's like, why is he doing that? Well, it's because it comes up later, and we'll use more of this notation to help us out with some things moving forward. Okay, so another example, like that last one, we used implicit differentiation, but we really didn't need to because it was easy to get that to say y equals, right? You could have just moved it over, whatever. Now this one, if you try to get this to say y equals, you can, right? But it ends up being, you know, y equals plus or minus the square root of 1 minus x squared. I'm not super excited to take that derivative, right? Plus the whole plus or minus things means that it's not a function and you'd have to take two derivatives, one for each part. Yeah, that doesn't seem like a good way to go. As we look here, to find the dy dx using implicit differentiation is going to be really easy. And what implicit means is kind of start with what you have usually. Sometimes you reorder it, it might be easy, but it means that we're going to use the chain rule. Now, where would we use it? Well, this is just, we know this derivative is just 2x, right? But this one, y is doing what u used to do with the chain rule. So we know if you had u squared, so if you had the derivative with respect to x of u squared, right, we know we would get 2u times du dx, correct? That's the chain rule. You do the outer, the squared, you do the inner. We're doing the same thing with y here. So what's the derivative? So to find the derivative here, we'll take the derivative, really show a bunch of work here. Derivative of each term with respect to x. Okay, so we have that. That's a pretty awful looking d right there. But we get this. Now, we know the derivative with respect to x of x squared is 2x. Now, the derivative of with respect to x of y squared would be 2y times dy dx. And then the right-hand side would just be 0. Okay, so now to find, in this case, we're able to, we're going to actually write dy over dx equals. So we'll subtract 2x from both sides. We will divide both sides by 2y. And we get that the derivative of y with respect to x is negative x over y, or negative x over y. So that would be our derivative of y with respect to x is negative x over y. When we're doing implicit differentiation, it's okay to have x and y in your answer. Now you wouldn't want to have dy over dx in your answer because that's not, right, you can't define the derivative in terms of itself, but this one you could. So if you had to write the equation of a tangent line, right, they might have to give you x and y, but like in this one they wouldn't. If they gave you one of them, you could find the other one up here in the original, and then you could plug that original, that point of tangency in here, and we could find that. We'll try one of those today. Okay, so for our next example, we have this function which, unlike the first one, which was a parabola that we looked at today, or the last one, which was a circle, I don't know what this is. This is some bizarre shape. I don't know. It's x cubed plus y cubed equals 6xy. Now, if we're going to find this derivative, I can't really solve this for y, right? You're not going to get this to say y equals without having the y on the other side. So we have to use implicit differentiation here. So what we're going to do is we're going to take each term and take its derivative with respect to x. So that means we do the derivative with respect to x of x cubed, and then the derivative with respect to x of y cubed, and then the derivative with respect to x of 6xy. So here, this is real straightforward. This is our new chain rule, implicit differentiation thing. This is going to be a product rule, right? Because 6 is a constant. You could put it, I'm going to put it with x. We'll say 6x is part of it. The second function is y. Right, so we have to keep that in mind. So let's kind of work through it here. We're going to get 3x squared plus 3y squared, but here's what you want to notice. Since the variable of integration, or of differentiation is x, these variables don't match, correct? So whenever they don't match, it means you have to do the chain rule, which means first we're going to deal with the y cubed, then we take the derivative inside, which is y. So we just say times dy dx, like that was part of what we were looking for. On this right-hand side, we'll go out to the side here. I said we were going to use the product rule here for this. So we get that u is 6x, u prime is 6, v is y, and then v prime is going to be dy over dx, because we know we're using this differential notation because we need it for later on in this problem. So we get this. So when we put these together, we get 6x dy dx plus 6y. So u times v prime plus v times u prime. So now we have this. Now our goal is to find dy over dx, so we have to rearrange this to where we get dy over dx equals. And if you think back to solving, what that means is we're going to get one side, anything with the dy over dx is going to be on one side of the equation, anything without is on the other side, and then we'll factor it out. So to do that, I kind of like this side over here, right? So we're going to say 3y squared dy dx minus 6x dy dx. So I subtracted 6x from both sides, 6x dy dx from both sides. Then over here, we're going to get 6y minus 3x. I subtracted 3x from both sides. We okay moving there? Just a little algebra, right? So now at this point, we'll factor out dy over dx. So I just did 3y squared minus 6x is what's left over. We still have this right side here. And then then what we'll do is, since we have what we're looking for multiplied by a quantity, we're just going to divide both sides by that quantity. So we'll get the derivative of y with respect to x is 6y minus 3x squared over 3y squared minus 6x. We can here, because there's a common factor of 3 on top and 3 on bottom, we could simplify this definitely. So we could say, if you factor the 3 out of top and bottom, 2y minus x squared over y squared minus 2x. But once you get to there, there's no more canceling that can happen. And really that's not. Does it make sense? There's a factor of 3 on top, 3 on bottom, factor them out, cancel it. So notice we're done because we have dy over dx equals. And the right-hand side is just in terms of, x's and y's, which is fine. So this would give us, so if we had this equation, right, and you wanted to find like a tangent line, right, you'd plug the point of tangency, the x and the y value of that point, into here, and that would give you the slope, and then you could write your equation of the line. Okay, so there's our third example. Again, it's a second derivative, which you're used to seeing probably as y prime. But it would also be the derivative with respect to x twice of y, is the way you might look at that also. So with this, we're going to go ahead and take the first derivative, because that's always the first step to find the second derivative. So to do that, take the derivative of x to the fourth with respect to x is just 4x cubed. And this will give us 4y cubed times dy over dx, right? So when the variable that you're taking the derivative of doesn't match what you're taking it with respect to, it kicks out this extra term. That's the chain rule. And then that equals 0. So 4y cubed dy dx equals negative 4x cubed. Looking okay so far? And then we get the derivative of y with respect to x equals, that'll be negative x cubed over y cubed? Does that seem believable? All right, so now that we're here, that's our first derivative. We want to find the second derivative. Okay, so with this, we're going to say, now can we just take the derivative here and get this piece? Sure, the left-hand side is the way we want it now. This would either be as it's written, it would be a quotient rule, right? Or we could reverse it and make it into a product rule. It doesn't really matter, just whatever your preference is. I'm going to try to leave it as a quotient rule. Just see what happens here. So for this one, we'll get, if we look at this right-hand side here, we're going to say that u is negative x cubed. So u prime would be negative 3x squared. Is that okay? And then v is y cubed, and v prime would be 3y squared dy dx. Does that work? All right, so let's go ahead and write this then using our quotient rule. So the derivative, the second derivative with respect to x of y, or y double prime, would be v, which is y cubed, times negative 3x squared, minus u, which is negative x cubed, times 3y squared dy dx, over v squared, which is y cubed, squared. Kind of check my work here. Yeah, everybody's look good so far? I mean, it looks bad, but I mean, does it look correct? Ish? Believable? All right. So at this point, let's go ahead and clean that up. I'm going to say negative 3x squared y cubed plus 3x cubed y squared dy over dx over y to the sixth. Now, we want to find the second derivative. We really don't want the first derivative hanging around in here. So what we're going to do at this point is we know that dy over dx is equal to negative x cubed over y cubed. Does that follow for everybody? So that's going to make a improper fraction, which I'm not loving that. So let's kind of doctor this up a little bit first. Let's go ahead and use some negative exponents to maybe help us understand what's going on here a little bit better. Okay, so if you take this, we're going to put a y to the negative sixth in both of these, basically. There's a way we could look at this. So you could say this will be negative 3x squared y to the negative third. Again, I had a y cubed on top and a y to the sixth on bottom. That's a y to the negative third on top. And then 3x squared y to the negative fourth dy dx.
3x cubed, right?
Oh, 3x cubed, thank you so much. 3x cubed, and then y to the negative fourth, and then dy dx. Now, can I replace this? Now I'm going to go ahead and replace this. So we get, this first piece is good. And then here we're going to get 3x cubed y to the negative fourth times negative x cubed y cubed. Right, so again, I just took this piece out and replaced it with this fact right over here. Right, that's all just a substitution. Right? We had dy over dx. We know from our first derivative that dy over dx equals negative x cubed over y cubed. This does not seem like it's getting much simpler looking. And then we're going to get negative 3x squared y to the negative third plus, well, it'll be minus, wouldn't it? Because there's a negative and a 3. Let's write this as 3x cubed y to the negative fourth x cubed from right here. This would be a y. If I moved it up, it would become a y to the negative third. So I'm just trying to make little steps to make this easier for myself because it doesn't feel super easy there. Hopefully it's getting easier. So now here, this is just an x cubed times x cubed, which will be x to the 6th. This is a y to the negative. You add the exponents. So we're going to get negative 3 x squared y to the negative 3rd minus 3 x to the 6th y to the negative 7th. Again, I just wrote that again. Add the exponents. X cubed times x cubed is x to the 6th. Y to the negative 4th times y to the negative 3rd is y to the negative 7th. Yes?
Can you do it the way of the product rule? Because I tried to do the, or not, yeah, the
Yeah,
product
let's
rule.
do the product rule. Okay. Yeah, so a request, we do take requests. Let's try the product rule, right? Let's keep this over here to see if it agrees with our next answer. Does that sound reasonable? Or here, I could even leave that up there a little bit. Well, yeah. Is that okay to do the product rule here? All right, so with the product rule, before we do the derivative, I would go ahead and say that dy over dx equals negative x cubed y to the negative 3rd. True?
Is it okay if I see the counts?
Is that good? This is equivalent to this? Okay, so again, if that all seemed really confusing, it is, but this is a different way, right? So maybe this will be a less confusing way to get you the comparable answer. So with this, I still have a product, correct? So I still need to do u and v and all that stuff. So here I'm going to say that u is negative x cubed, u prime is negative 3x squared, and then y to the negative 3 would be v. So that derivative would be negative 3y to the negative 4 times dy over dx. Now, it wouldn't be wrong to actually put dy over dx in here at this point, which might make it a little bit easier to kind of work with. So if we did that, that would be negative 3y to the negative 4th times negative x cubed y to the negative 3rd. Does that seem reasonable to everybody? And that's going to give us, 3 x cubed y to the negative 7th. Okay, so now let's do our product rule. So the derivative, the second derivative, is this all going to fit? So let's see, we get negative x cubed times 3x cubed y to the negative 7th plus y to the negative 3 times negative 3x squared. I'm really hoping it matches this other answer. If it doesn't, this is going to be very discouraging. And that's going to give us negative 3x to the 6th, y to the negative 7th. Well, I like that. And this is going to be negative 3x squared y to the negative 3rd. So that's the same answer, right? That was so much easier. I would use the product rule next time. That was a mess, right? Quotient rule, not as much fun. I never really thought about this, but this, if you know you're doing the second derivative, this substitution here is, I think, what really made it a lot easier. To go ahead and when you get that dy over dx, if you know what it is when you're working through even the product or the quotient rule, it's probably going to make it a lot easier. So I would recommend you do that. I'll probably do that in the future.